Good morning, friends. Today we are discussing on laminar flow through circular pipe. For the flow of viscous fluid through the circular pipe, there are four equations to be determined. The equation which is showing the velocity distribution across a section, then the ratio of maximum velocity to the average velocity, then shear stress distribution. The fourth one is drop of the pressure for the given length to be determined. These four equations together help us to arrive at Hagen-Poiseuille's equation. So when the flow will be called as laminar flow. So when the Reynolds number, that is Re, is the ratio of rho Vd divided by mu. So where Re is the Reynolds number, rho is the density of the fluid flowing through the pipe, V is the average velocity of the fluid, uh, D is the diameter of the pipe, and mu is the viscosity of the fluid. When Reynolds number is less than 2000, the flow through the pipe is called as laminar flow. So because of the viscosity of the fluid, the flow is considered as laminar. So now we have taken a pipe here of diameter capital D, so that the radius is capital R. The flow is taking place from left to right. Now, as I said earlier, so there are four things to be determined: the velocity distribution, shear stress distribution, drop of pressure for the given length, and ratio of maximum velocity to average velocity. We will see one by one. Now taking a shear stress distribution. So consider a horizontal pipe of radius capital R. The viscous fluid is flowing in the pipe. So we are considering a fluid element of radius here small r. So sliding in a cylindrical fluid element of radius, so that is smaller with the thickness dr. So the fluid is flowing through this cylindrical element. So having the radius from here to here, it is smaller and the thickness is dr. So that means in the entire pipe having the radius capital R, we have considered an elemental ring of radius smaller and the thickness is dr. So the length of the fluid element, though the fluid is flowing from the inlet and exiting here, so I am considering only one part of that fluid, so that is the fluid element of radius smaller sliding in the cylindrical fluid element that is having the radius smaller plus dr. The length of the fluid element is delta x. So forces acting on the fluid element now, so it is uh, uh, the in the direction of the flow I have the pressure force. So pressure is P into cross sectional area of the pipe, so that is pi r square. So here the fluid element is having the radius smaller. So if I consider the fluid flowing through this element, so that is having the area, so that is pi into small r square. So pressure is equal to force by area. So force is equal to pressure into area. So pressure force is now P into pi r square on the face AB. Now pressure force on the face CD, that is on the other face. So it is P plus del P by del X into dx pi r square. So that is on the face CD. Now shear force. So that is there will be resistance against the flow from the wall of the pipe. So that is I have the shear stress, so tau into, so this area of the element. So the perimeter of the fluid element is dr, having the length dx. So area of the element now is now 2 pi r into dx into shear stress, because stress is equal to force by area. So force is equal to stress into area. So the three forces acting on the fluid element are shown here. Now summation of all the forces in the direction of the flow to be made 0. So now in the direction of the flow we have the pressure force, so that is P uh, that is P into pi r square. Then we have the pressure force on the face, so that is CD here, so that is P plus del P by del X of del X into pi r square, that is acting from right to left, so that's why it is taken minus sign here. Then the pressure force, so that is also acting from right to left, so that is tau into 2 pi r into delta x. So that is, both of them are acting from right to left, they are considering minus sign. So summation of the forces is made to 0. So I am getting the shear stress equation as minus del P by del X into R by 2. Now velocity distribution, so that is tau is equal to mu into du by dy. So my velocity equation, Newton's law of viscosity. So we are getting the velocity distribution equation. The Newton's law of viscosity says that tau is equal to mu into du by dy. That is, my shear stress is proportional to velocity and directly proportional to the distance. That is, if I consider this fluid element which is at a distance of now capital R minus small r. So the distance of the fluid element is now, so this is from the wall of the pipe to the axis of the pipe. So the distance is capital R. So from here to here, so the distance is smaller. So the distance of the fluid element from the pipe wall is nothing but capital R minus small r. So that is what it is written here. Y is equal to capital R minus small r. So differentiating my y, so it is dy. So since the radius of the pipe is constant, but the radius of the fluid element small r will be changing. So that differentiating this r. So we are getting minus dr here. Substituting dy as minus dr, we are getting shear stress is equal to minus u into du by dr. Substituting this tau here, so we have this tau is u into mu into du by dr is equal to, so we have minus del P by del X into R by 2. So we have substituted the value of shear stress in this equation, shear stress equation. Then so we are getting the equation like this, rearranging the terms. Then integrating this, integration of du by dr is nothing but here taking this dr to the other side. So it is integration of du, so that is u here. So is equal to here, keeping this entire thing as constant, integration of r is nothing but r square by 2. So totally the denominator becomes 2 into 2 mu, so that becomes 4 mu. So we have the integration constant c here when small r is equal to capital R. So that is when we take exactly the wall of the pipe here. So it is said that my velocity u is equal to 0. That means exactly at the wall pipe, so the velocity of the fluid flow is 0, whereas we consider that the velocity is maximum at the axis of the pipe. So velocity at the pipe wall is 0. So considering u as 0, so and taking c as constant of integration, so substituting u as 0, so solving it, so we are getting c here, that is constant of integration. So substituting this c, that is the constant of integration, in the velocity equation, so we are getting u velocity equation. So that is called as equation of parabola, because we have the power of 2 in the equation. So it is said that the velocity u is varying with r square, that is the power of 2 for the radius of the pipe. So that means the velocity u is directly proportional to